Hello and welcome back. Today I want to continue talking about the Class A amplifier by designing, simulating and building a single transistor wideband common emitter amplifier. I mean, how hard can it be? Anyway, afterwards of course I will be testing the circuit out to verify its actual performance, like how linearly does it follow an input signal and just how hot does it get. And if you're curious, then keep watching. So, first things first, what is the design goal? Well, as with all the linear amplifiers that I will be building in this mini-series, I want to deliver half a watt into a 50 ohm load. Since as a test load, I will be using a termination resistor, and if I'm delivering more power, I'm afraid I might break it. And as main amplifying element, I will be using a BD135 medium power NPN transistor that should have a high enough transition frequency to allow the amplifier to work up to a few megahertz. So, let's start calculating the components. Now, the general schematic will look something like this. So I will be using a common emitter amplifier configuration with a resistor network to set the bias point and an emitter resistor to stabilize the gain and provide negative feedback. Finally, an inductor will be placed in the collector to maximize efficiency. So this general topology should allow a maximum theoretical efficiency of 50%. And finally, we will have input and output DC isolation capacitors to isolate the input signal source and the output load, and a supply voltage. Now, I won't be using any impedance matching, first of all to keep things simple, but also to get a wide bandwidth frequency response. So to start calculating the components, let's start with what we actually know. So knowing the output load value and the output power, we can work out the output voltage that we need. So we will need a 5 volt RMS voltage, which translates to a 14.14 volt peak-to-peak voltage. Now, even though this configuration can supply double the supply voltage on the output, we will need a bit more than 7 volts to supply the circuit. So the supply voltage will have to be half of the output load peak-to-peak voltage, but we also need to account for the minimum collector-emitter voltage drop and the voltage that's dropping on the emitter resistor at peak current. So to work out the actual supply voltage, we will need 7 volts for the load. For the collector-emitter voltage, we can take a value of 2 volts, since the datasheet does provide DC current gains at this specific value, so we'll choose this. And for the emitter resistor, well, this component has two purposes. On the one side, based on this component and the load value, we can set the voltage gain of the circuit. But secondly, the larger the voltage drop that occurs on this resistor, well, the more heat gets dissipated, but also the exact base emitter voltage, which is temperature dependent, becomes less important in analyzing the stability of the circuit. So by having large emitter resistor voltages, we can make the circuit more stable. So we'll set this voltage drop to 1 volt. So the total supply voltage will end up being 10 volts. Next, we need to calculate the static operating current. So the point around which the current will oscillate as the amplifier is amplifying. And well, this needs to be half of the peak current. So we need to work out that thing first. So this can be determined based on the peak-to-peak load voltage and, well, the load value. And this gives us a peak current of 283 milliamps. So knowing this, we can work out the static current, which is half of this, so 141.5 milliamps. Now we can start working on the components of the circuit. So first, let's start off with the emitter resistor. And we can calculate this based on the voltage drop that we've set of 1 volt and the peak current of 283. So this gives us a value of 3.53 ohms. Now, this isn't really a standard value, so I'll be using a resistor of 3.3 ohms since I actually have this component. Based on this value and the load, we can now work out the expected voltage gain. So based on the load value and the emitter resistor, this gives us a voltage gain of 15, but in reality we'll be getting slightly lower gains because of the equivalent resistor present in the emitter of the transistor. So we don't just have the emitter resistor on the outside, we also have a small resistor inside of the transistor. Finally, we can start working on the biasing resistors. So first, let's work out the exact voltage drops on each of these. So first, the voltage drop on R1. this will be equal to the voltage dropping on the emitter resistor plus the voltage dropping on the base emitter junction. So we can take a base emitter voltage of 0.7 volts, and for the emitter resistor we can work out the voltage drop based on the static current. So we're getting a total voltage drop on R1 of 1.16 volts. Now the voltage drop on R2 is, well, the supply voltage minus whatever is dropping on R1. So we get 8.84. Next, we need to work on the currents. And the first thing to calculate is the base current of the main transistor. So this is calculated based on the collector current and the gain factor. So for the exact transistor that I'll be using, I have a minimum gain of about 100, and the static collector current is 141 milliamps. So this gives us a base current of 1.41 milliamps. Now, to ensure stability in the circuit, a common way of calculating the two resistors is to set the current going through R2 that is 10 times the base current, and well, the current going through R1 is 9 times the base current. So 1 times goes through the base. So by this logic, we can work out that R2 will have a current of 14.1 milliamps, and the current through R1 will be 12.7. Now we know the currents, we know the voltages, so we can work out the actual resistor values. And again, we're getting non-standard values, so I'll be using a 620 ohm resistor and a 91 ohm resistor for the two bias setting resistors. Final thing we can do is calculate the power dissipation. So since the amplifier will consume roughly the same amount of power whether it's doing something or not, we should calculate how much power is being used in the static point, and we can assume that most of this power is dissipated on the transistor. So we're getting almost 1.5 watts. So definitely we should have a heatsink to make sure that the transistor doesn't self-destruct. Final thing to do, we can work out the expected efficiency. So we know the output power of half a watt, we know the input power of 1.41 watts, and this gives us an efficiency of about 35%. So it's not 50%, but it's not that bad either. So finally, just to make sure that no errors were made during these calculations, let's check the circuit in a circuit simulator. So here is the circuit that we've just calculated. Now I added in the various resistor values that we've worked on, and as transistor model, I used one that I found online. So I found this website that's somehow related to Philips, Philips being one of the manufacturers that used to produce this transistor in the past. And the nice thing about this website is that they are providing a model for the BD135-16. So this is a specific gain group, and this is the transistor from which I have the practical one. So I'll be using this model, and I'll be leaving a link to this in the description, so if you want to check this website out. So now, back to the circuit. First thing to check is the static operating point. That's why there's no input or output signal here. If we run the circuit, we can check the current running through the collector, which is around 130 milliamps, slightly lower than what we've calculated. And other than this current, the total current passing through the circuit is about 144 milliamps. Now, regarding the current consumption, it's important to point out that the current simulation is running at 25 degrees Celsius, but we can also simulate at another temperature, say 60, because the Class A amplifier will heat up in its operation. So we can expect the transistor to be a bit hotter. So if we now look at the collector current, we can see that the 130 milliamps is the behavior at 25 degrees, but there's also a nice blue line up here at around 142 milliamps, which is at 60 degrees. So the hotter the transistor will be running, the higher the collector current. Now, other than waiting for the transistor to heat up, another thing that we could do is increase the value of R1, but for the moment I'll leave things as they are. So the higher the current at which the transistor is running, the lower the gain it will have. So that's why I'm leaving the circuit as it is. But now I'll leave the temperature at 60, and if we now add in all of the other components, so other than the main amplifier, an input signal, coupling capacitors both on the input and output, a load, and the inductor. Now, without going into too many details about these other components, regarding the collector inductor, more is better in general. So the more inductance this inductor has, the lower the frequencies that the amplifier will be able to handle. Now, on the other hand, a very large inductor will also have a lot of parallel capacitance. So there's a balance that needs to be found here. Similar story with the coupling capacitors, larger is better. The larger the capacitor, the lower the bandwidth is pushed to low frequencies. So anyway, if we run the circuit, we can look at the voltage present in the collector. We can see that for the specific signal that I'm inputting, it's dropping to almost 3 volts, and the voltage on the emitter resistor is rising up to about 925. So we're getting about 2 point something volts drop on the collector emitter of the transistor. We can also look at the signal on the output, so it's almost 14 volts peak to peak, and this is giving us an output power of about 450 milliwatts, so slightly lower than 500, but it'll do. And we can also perform some automated measurements on the circuit. So first of all, I prepared this set of measurements to measure the efficiency, and we can look at that in the error log. So we can see that for this configuration, we're getting about 28.6%. So it's not great, but it's more than 25. Now I also prepared this other set of measurements. So this is to measure the voltage gain of the circuit by measuring the ratio between output and input peak-to-peak voltages. And again, this is present in the error log, and we're getting a value of about 13. So it's less than the 15 that we would be getting just based on the resistors, because we also have an equivalent resistance in the emitter of the transistor. Finally, we can look at the output signal in an FFT spectrum to see just how clean it is. And we can see that we are getting some extra harmonics, but the difference between the first two peaks is around 35 decibels. So we can call it decently clean. Now, other than the transient simulation, we can also perform an AC simulation. So just to quickly see the bandwidth of the circuit, and if we look at the output, we can see we are getting a fairly flat response, starting from around 10 kHz up to around 10 MHz. So over 3 decades of frequency. So this will be quite a decent wide bandwidth amplifier. So now that we've seen that it works in the simulator, it's time to test it out in real life. Now, without going into too many details, this is a really simple design after all. Here is the finished circuit. It's quite compact, and other than the large heatsink for the power transistor and the large inductor, most components are quite small. I did, however, use through-hole components for the resistors to better dissipate the heat, but everything else is surface mounted. Also, other than the components already discussed, the circuit has a set of supply decoupling capacitors and filters to reduce any noise that would be otherwise going out onto the supply lines. And that being said, it's time to test things out. So here is the first setup that I've prepared. I've got my circuit, it's being supplied from my power supply back here, and I'm passing the current through an ammeter to get a more precise current measurement. My signal generator will be providing the signal into the circuit, and the output is connected to the oscilloscope's first channel, where I have my 50 ohm termination resistor. So first thing to check out is the current consumption of the circuit. So this should be our very first indicator to see whether the circuit is working as expected or not. So when I connect the power supply, we are getting about 139 point something milliamps, and we can see that this current is increasing. So as the transistor is warming up, we are getting more and more current consumption. So this is very close to the total current consumption that the simulator was telling us about. Now at the moment, there is no output signal, we can see it's flat, and if we turn on the signal generator, so we're at 446 milliamps, with an output signal, not much has really changed. So we are still in the same region, we see that current is slowly decreasing. So again, as some of the power gets delivered, transistor is getting slightly colder, so we have a small shift in the current consumption. Now if we look at the actual signal, we can see we are getting a pretty nice sine wave. We can play around with the amplitude a bit, so if we increase the amplitude, we can see a bit of distortion occurring on the bottom side, also on the top side. So if the signal is small enough, then it's nice and symmetrical, but if you increase it too much, then you start to get some problems. So we'll leave it like this. So at the moment we're getting 4.67 volts RMS onto the 50 ohm load, and this is giving us a power of 436 milliwatts. Now the first observation to make about this is that if you want to make an amplifier for half a watt, design it for a bit more. Otherwise, you might run into distortions and other problems. Now, anyway, the current signal that we are looking at is running at 2 MHz. So the other thing that we can play around is the input signal frequency. So we can go up to 3, 4, 5, it's starting to decrease, so as frequency increases, we start to get a smaller signal, so this is at 5 MHz. But we can also go the other way, so 1 MHz, let's just zoom in a bit more, 400 kHz, 200, 100. We can see that we are still getting roughly the same amplitude, and we can go even lower. So maybe you can already hear it, it's at 10 kHz right now, and even lower, and now the amplitude drops a lot more. So you can see that we are getting a very wide bandwidth, but the best way to test it is not like this, but rather with a Bode analysis. So for this measurement, I'm using a signal amplitude of about 900 millivolts, and I'm running a sweep between 3 kHz and 50 MHz, just so we can see a nice and wide response. And if we look at the measurement, so we have 10 points per decade, we can see we are getting a very nice, very flat response, all the way up to almost 20 MHz. So between this 10 kHz point, we're getting an amplitude of 22 decibels. It stays relatively flat, 22, 22, 22, all the way up to 15.85 MHz. And then it slowly drops off. So it did manage to make a very nice, very wideband amplifier. Next we can look at modulation performance. So I left in yellow the input signal, in blue the output. I'm running at 500 kHz and the 500 millivolt input signal. So there's no point in checking out frequency modulation, we already saw that the circuit has a very wide bandwidth. So let's look at some other types of modulation. First off being amplitude modulation. So we can see that the input signal and the output signal are almost identical in shape. Maybe there's a bit of distortion here on the bottom of the blue signal, but that of course can be adjusted by the input signal amplitude. Otherwise the two signals are quite identical. Next we can try out phase modulation. So this is a type of modulation in which the phase of the signal suddenly changes. And we can see it on the input signal, so we've went from one phase to completely different phase, frequency stayed the same, but we had a very sudden change, and we can see the same thing on the output. So the output is inverted, but we can see that the output signal very closely followed the input signal, so there was no lag or nothing. The output followed the input exactly. Final thing to look at is ASK type of modulation, amplitude skip keying, and here again we can see that the input signal and the output are very well matched. So there's no delay in the output signal, it's following the input signal identically, there's no variation in amplitude, it starts off directly at full amplitude and then turns off right as the input signal disappears. So we are getting an all-around good performance with any sort of signal modulation. Now, final thing to do is test thermal performance. So right now there is a signal passing through the circuit, and I'm measuring the temperature on the transistor, on the screw that's holding the transistor in place with a thermocouple, so we're getting about 51, 52 degrees Celsius. We can also look at the circuit with a thermal camera. So we can see the main hot element is the transistor and the heatsink, but there's also a couple of resistors in there which are also heating up. So when designing such an amplifier, it's also important to take into consideration that you're dissipating power not just on the main amplifying element. So you need to take care with also the other components. Now, we can also look at what happens with the amplifier if we turn off the signal. So right now the signal is off, current consumption stayed roughly the same, but since there's no more power being delivered to the load, we should be seeing an increase in temperature, since now all of the consumed power is dissipated on the transistor. So as with any thermal behavior, it takes the time it takes, but we can see that the temperature is now slowly increasing. So we're at about 54 degrees and it will probably increase a bit more. Now the circuit works, it's performing as expected, but there are some interesting things to point out regarding what could have been done differently, specifically regarding the efficiency. So the main non-ideal elements which are pushing us away from the maximum theoretical efficiency are the minimum collector emitter voltage not being 0 but rather a couple volts, and also the voltage drop on the emitter resistor. Now, you can use better transistors and these voltages will drop slightly, but the fact remains that you will still have 2 to 3 volts out of the supply voltage being lost because of these non-ideal behaviors and the need for feedback. Now, if you lose 3 volts out of 10 volts, it's a 30% loss. But if you lose 3 volts out of, say, 100, it's only 3%. What I'm trying to say is that these voltages are relatively fixed and independent of the supply voltage. So as long as the correct impedance matching is used on the output side, you can greatly improve efficiency simply by using higher supply voltages. In the end, the Class A amplifier provides the benefit of high linearity, which is highly prized in audio applications, and also allows the possibility to amplify any sort of modulation, specifically useful when talking about radio frequency signals, but it also has the important benefit of simplicity. It can be built around a single amplifying element. If the efficiency is not of big concern, this type of amplifier is extremely useful and important and has a multitude of applications. Now, if only there was a way to do something about that efficiency. What's the next letter after A? Anyway, that will be it for today. So, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos. And see you next time. Bye bye.